When the birefringence of a uniaxial mineral having refractory indices of 1.658 and 1.468. Do you know birefringence? It is high Ri minus low Ri. High refractive index minus low refractive index. So your high refractive index is 658 minus 1.486. So the if you subtract it, it will be 0.172. 0.172. So this will be the answer, 0.172. Then crystal phase of the following intercept to the crystallography axis: 1A, 1A, half A3, infinite C. Write down again here. 1A1, 1A2, half A3, infinite C. So you have to calculate the Miller-Wallace indices for this phase. Just take the reciprocal one by one, then you take the reciprocal one by 2, 1 by infinity. It will be 1, 1, 2, it will be 0. 1, 1, 2, 0. So just take the reciprocal. The total number of mirror planes in the point group is given 4 by m, 3 by 2 by m. So I have to find out what is the total number of mirror plane present here. So this is the hexaoctahedral class, belongs to isometric system. You just write down 3, 4, 6 above it. So here we have 3 axial mirror plane and 6 diagonal mirror plane. Total we will find 9 mirror plane. So answer will be 9. So the calculate the average atomic weight. So first the isotope rubidium 85, rubidium 87, they have an atomic weight of 84.912, 86.909, and they have abundance of 72.17%, 27.83%. So rubidium 85, when it is 100%, it weighs 84.992. Now it is the abundance is 72.17%. So you have to calculate the atomic weight of the rubidium 85 when it has the abundance of 72.17. Then we have to calculate rubidium 87 weight when it has an abundance of 27.83%. So, you can say weight of rubidium here, it will be 84.912 into 72.17%. Then weight of rubidium 85, then weight of rubidium 87, it will be 86.909 into 27.83%. So isotope of rubidium, when it has abundance of 72.17, it has weight of 61.280. Then weight of rubidium 87, it has the abundance is 27.83%. It is 24.18077%. So now, what will be the average atomic weight of rubidium? So average atomic weight of the rubidium will be, it will be weight of rubidium 85 plus rubidium 87. It will be 61.280 plus 24.186. You can consider other decimal also. So you have to give answer up to 3 decimal. So only take 3 decimal, 85.467 approximately. This will be the average atomic weight of the rubidium. So average atomic weight, how we will calculate? See, can write down this also. Average atomic weight. Isotopic abundance. Isotopic abundance into atomic weight. So the number of isotope you have to calculate these things, then add them. So isotopic abundance of rubidium 85 into its atomic weight, then isotopic abundance of rubidium 87, then its atomic weight, then we'll add them to get the average atomic weight. So isotopic abundance into atomic weight, that will give the weight of the isotope. Then after getting that weight, we'll just add the weight of the isotope to get the average atomic weight of the element. Then a mineral has weight of 4.5 gram in air and 3.2 gram in water. Assuming the density water to be 1 gram per centimeter cube, the specific gravity up to 2 decimal. So write down the formula: specific gravity, weight of mineral in air by weight of mineral in air minus weight in mineral in water. So weight of mineral in air, it is given 4.5 gram divided by 4.5 minus 3.2 with 3.46. It will be 3.46. From the given equation, calculate how many moles of magnetite will be produced by the reduction of 1 mole of hematite. So this type of question, when you see, first you have to see the equation and you have to identify which is your hematite, which is magnetite. This one is your magnetite, this one is your hematite. So in this equation, it is written 6 Fe2O3. It is producing 4 Fe3O4 plus O2. That means 6 moles of magnetite, hematite produces 4 moles of magnetite. From this equation, you can see 6 moles of Fe2O3. When it will break, it will produce 4 moles of Fe3O4. So we have to calculate how many moles of magnetite will produce from 1 mole of hematite. So 6 mole will produce 4 mole. So 1 mole will produce 4 by 6 moles with 0.66. Up to 3 decimal, you can write down 0.666. Based on the ideal end member formula of diopside. So what is the formula of diopside? CaMg Si2O6. So you have to calculate the mole proportion of Ca. So in this formula we have CaO, MgO and SiO2 oxides are present. So CO, it is present 1 mole, MgO it is present 1 mole, SiO2 it is present 2 moles. So CO it is 1 mole, MgO it is 1 mole, SiO2 it is 2 moles. So we have to calculate the mole proportion of CO. So number of moles of CO, number of moles of CaO divided by total moles into 100. The number of mole of CO, it is 1. Total mole we have 1 plus 1, 2, that is 4 into 100. That will be 25%. Will be 25%. Next comes to the following schematic diagram. The aluminum silicate, the triple point, it is a 4.50 kilowatt. Okay. And the temperature at this point is 823 kilowatt. Okay. So a reaction is proceeding here where andesite eliminate, they coexist with each other. So when the reaction is proceeding here, the temperature decreases from 823 Kelvin to 923 Kelvin. Okay. And the slope, it has a negative value of minus 18.22 bar per Kelvin. So each change in pressure, each change in degree of Kelvin minus 18.22 bar pressure is decreasing. So it is showing that we have to calculate the pressure at 923 Kelvin. Okay. So this indicates that each 1 degree change in temperature or 1 degree change, 1 Kelvin change in temperature, the pressure is decreasing minus 18.22 bar. So here pressure is decreased 100 Kelvin. So it is from 1823 to 1923. So pressure decreases 100 Kelvin. So in 1 Kelvin, temperature decreases 18.22 bar. So in 100 Kelvin, it will decrease 18.22 into 100 bar. It will be 18.1822 bar. And if you convert it into kilobar, it will be 1.8 kilobar. It will be 1.8 kilobar. Then from this point to this point, the pressure decreases 1.8 kilobar. So initial point we have temperature 4.50. From this point it decreases 1.8 kilobar. So 4.5. So I have to just subtract 4.5 minus 4.5 minus 1.8. So it will be, this I have to write down 1.822 kilobar. Okay. 1.822, it will be 2.678. Or you can write down 2.67. 2.67. Understood? So initially there are 4.50 kilobar pressure, when temperature decreases by 100 degree. So for 1 degree of temperature decrease, pressure decreases 18.22 bar. So in 100 it is decreases 1822 bar or 1.822 kilobar. So after decreasing 1.822 kilobar, the pressure is now 2.67 kilobar and the temperature is 923 Kelvin.